This is part 2 of homework section 4.2, picking things up at problem number 5. I'm going to skip a few of these because they're pretty similar. So I'm going to do problems 5 and 7 remaining from this first section. Alright, so getting back to things, we're going to take the derivative and use that to analyze where it's increasing, decreasing, and where my local minimum maximums are. So the derivative of e to the 2x is going to be e to the 2x times the derivative of 2x, which is 2. I'm going to set it equal to 0. And we should know that this is impossible. If not, we can do a little math to solve for it. So I divide by 2. And then in order to get rid of e to the 2x, I would need to take the natural log of both sides. And here, if you didn't notice it before, we should notice it at this point that natural log of 0 is impossible. So this is leading to no answers. So we get no critical values from setting the derivative equal to 0. And we should also know that e to the x is, the domain is all real numbers, so there is no number I can plug in here that's going to cause the derivative to be undefined. So what this means is I have no critical values whatsoever. So my sign chart is going to be pretty boring. Basically what it means is I can pick any number I want, and the slopes will always be whatever that slope is, as far as positive or negative goes. So I go to my derivative, I plug in any number you want, and I can clearly see that the answer is always going to be positive. So A, what are my local extremes? None. B, where am I increasing? Everywhere. And C, where am I decreasing? Never. And again, we should know that the graph of e to the 2x is going to look like some version of this graph with an asymptote. So we can see that the slope is always positive, which is what we found. Alright, so I'm going to jump to number 7. And we could kind of piece together this graph a little bit and figure out what it looks like. We'll do that at the end. Let's just see what the math tells us. One thing I should, though, pay attention to is my domain. I can't take the square root of a negative, so that means if I plug in negative 2, that gives me 0. Negative 3, that would be a problem. So it looks like negative 2 is the border, and we can go all the way to infinity. Okay, so now let's take our derivatives. Derivative 4 is 0. Negative, chain rule, 1/2 x plus 2 to the negative 1/2 times the derivative inside, which is just 1. So simplifying this down a little gives me, I'll leave the negative on top just for fun, 2 square root of x plus 2. Alright, so now we set this equal to 0, and I hopefully again can quickly see that there are never any times where the derivative is going to equal 0, but then I also want to find out about undefined. And so I take a look. The numbers I couldn't use before, the ones that would make the square root negative, I still can't use. So I don't need to really worry about those. But I do need to worry about dividing by 0. And that would mean x equals negative 2. So x equals negative 2 is my only critical value. It also happens to be the border of where I was going to check anyway. So making it an endpoint. So I was going to look at negative 2 anyway. So let's look at our sign chart, which isn't going to have anything on it except negative 2. And again, I can't check over here because that's not part of my domain. So I'm just going to plug in a number bigger than negative 2, like 0, I guess. And I plug it in to my derivative, and I get positive on the bottom and negative on top. So I'm always decreasing. So that means A, we'll come back to A. B, when is it increasing? Never. C, when is it decreasing from -2 to infinity. And then part A says, what are my local mins and maxes? So if I'm decreasing once I leave -2, that should make a local maximum at -2. And then I need you to find the y value. So again, why is that? I don't know where I'm at -2. Let's just say I'm here. Then as I leave -2, my slopes are negative, which means my graph is looking like this. So that means my point at -2 has to be a local maximum. The graph of this is pretty close to the one I just quickly sketched. It's going to be a square root graph. It's shifted over to -2. So looking at the equation, the +2 means it's shifted over. The +4 on the outside means it moves up. So from 0, 0, I went to -2, 4. And then instead of it being a normal one, where it looks about like this, I have a negative in front of my square root. So that means we're going to look more like this, which matches everything we found. Okay, let's move on to number 9 in this new section. Number 9 says, really it's the same instructions as before. Find the local extreme, the intervals in which the function is increasing, and where it is decreasing. The difference between the two is that the book wants you to use analytic methods for the first ones, and it doesn't really specify for this section. But, so basically what they're saying is, you can graph and find the answer if you want. I kind of like to overrule their instructions, and I'd like you to try this and then verify it graphically. So we're going to go ahead and go through the same process we have been doing, and that probably means I'll get through number 9 on this video and then stop. Alright, I'm going to consider the domain, and at x is 4, I'm good. At x is 5, I have a problem. So it looks like my domain is going to be -infinity all the way up to 4, including 4. If I plug in a negative number, it's going to turn to positive, and I'll be fine for my square root. So that means I'm going to be checking my endpoint at 4. Okay, so now let's take the derivative. I have a product rule, so the derivative of x is 1 times the second plus the first times the derivative of the second using a chain rule, multiplied by the derivative of the inside of -1. I'm going to clean this up, and this looks a lot like some of the problems we did in section 4.1 at this point. I have a negative, so it's going to become minus. I have an x on top, a 2 on the bottom, and a square root on the bottom. So it looks like I'm at 2 square root of 4 minus x. I need a common denominator. So this guy is going to get multiplied by the 2 and the square root of 4 minus x, top and bottom. And that's going to give me 2 times, the square roots are going to cancel each other out. So I get 2 times 4 minus x, excuse me, close that parenthesis, minus x over 2 square root of 4 minus x. Which gives me, let's do this in one step. 2 times 4 is 8. Negative 2x minus x looks like minus 3x over my denominator. Okay, so now it's time for critical values. So let's set the derivative equal to 0. And that's going to happen only when the numerator equals 0. So negative 3x equals negative 8. X equals 8/3. I also need to find out when the derivative is undefined. And that's going to be whenever the denominator equals 0. And that's only going to happen at x equals 4, because that'll cause a 0 in the bottom. And again, I'm only worried about points in my domain, so I already know that 5, 6, 7, 8 obviously won't have a derivative, but that's simply because those values aren't even part of my graph. So clearly I can't have a derivative there. Okay, so these are the points I'll put on my sign chart. So 4 is the upper limit of where I can go. And then 8/3 is going to be over here someplace. And so now I need to find my slopes in between these. So I'll plug in 0 to my derivative, because that's over here. On top I get 8, so positive. On bottom I get positive. And then between 4 and 8/3, 8/3 is 2 and 2/3, so let's plug in 3. On top now I have a negative, and on the bottom I have a positive. So I'm ready to go. Part A, I have a local max at the point 8/3, and then I'll leave you to find the y value. I have a local minimum at 4, comma, I think it's 0, yep. Because again, my slopes are negative right before I get to wherever I'm at 4, which means I've decreased to get down there, making it a minimum. Part B, where am I increasing? Negative infinity to 8/3. And part C, where am I decreasing? 8/3 to 4. Alright, that's at 11.5 minutes, so I'm going to stop, and we'll pick things up with number 11 on the next one.